record, then go to Zoom. Thank you for chiming in, Zoom refugees. Can you see it now?
Yeah, it's back now.
Okay, awesome. Thank you. All right. We'll try this again, see if it works. So, and we are recording. So let's have this NH2 minus and this alkyne. And then I'm going to ask, what do we expect in this equilibrium if we draw the conjugate acid of our base and the conjugate base of our acid? pKa of this acid is 25, pKa of this acid is 38. So who gets to lose their proton? The one that's 25, right? The one on the left gets to lose its proton. Strongest acid loses its proton, so yep, that's going to push the equilibrium over here. Now, when formatted that way, it's a pretty straightforward question to answer. However, as you know, I am evil, and so sometimes I will format the question in a slightly different way. I'm going to make up a molecule, I haven't thought anything of it until now. And then maybe let's have some horrible looking side chain here. Are we tired yet? Okay, that's close enough. So in a large molecule like this, I might ask the question, which protons can be removed with a certain base? Let's start with the conjugate base of ethanol or ethoxide. I will actually draw it out like this. Which protons can be removed by ethoxide? Okay, now that looks like a totally different question. It's not. It's the same question. It's just formatted a different way. So how do you do this? Well, you can go, I would start by trying to recognize any proton that has a pH that's acidic enough to worry about. All right? And the way you look for protons that have pKa's that are acidic enough to worry about is you look at the conjugate acid of the base, which in this case is ethanol, which I know has a pKa of around 16. So I'm going to be looking for protons whose pKa's are 16 or less. So how about a carboxylic acid? I could look that up. And this is where recognizing functional groups is going to help. You're going to do that a little bit in chapter 3, which we'll start today. Carboxylic acid pKa is 4. It turns out an OH group that's adjacent to a benzene ring, because of the possibility for resonance stabilization of the conjugate base, you get a pKa of around 10. We'll say that this sulfur group, actually you have a pKa around 7, and then this alkyne proton, you have a pKa of around 25, and then I guess we need to pay attention to the proton on the amine, which should have a pKa of 38. All right? So having identified the acids that we're willing to worry about, that show up on a pKa table from your text. The next question is, which of these could be removed by ethoxide? And to do that, you can do this slowly by putting ethoxide here in equilibrium with the functional group that you're interested in. Draw the conjugate acid and conjugate base. Choose the acid on either side of the equation and write down its pKa. Then you can answer the question exactly like we did above. Which acid loses its proton? The stronger one, the one with the lower pKa, right? So that means equilibrium favors this side of the equation where the acid has lost its proton. Does that make sense? So we can say, yes, this carboxylic acid proton could be removed by ethoxide, right? Well, we could do this again with the amino group. And draw the conjugate acid and the conjugate base. Line up the pKa's. Oh. So what do you conclude there? Can ethoxide remove a proton from the amine? No, not going to happen. All right? And this allows us to come up with, now if you do it this way, you're never going to get it wrong as long as you remember that pKa, lower pKa means stronger acid. But there is a shortcut that might be useful to you. And this is something that I say and then I write down and then I say it again. So we'll do that because I usually need to say it again 3 or 4 times. A base can remove a proton if the pKa of that proton is less than, and I'm going to insert a word here, mostly. Base can mostly remove a proton if the pKa of that proton is less than the pKa of the base's conjugate acid. I'm not sure if that helps. It may make it worse. Can I say it again? Yes. I'm not sure that helps. It may make it worse. No, not funny. A base can remove a proton if the pKa of that proton is less than the pKa of the base's conjugate acid. All right? So what does that mean? Once I've identified the conjugate acid of the base, and once I've identified all my acids, I just need to look for numbers here that are less than 16. Yes?
So what's the best way to identify the pK base? Because I feel like that's what would be the hard part.
Okay. Right, getting the pKa values. See, I got all the information up here. You got all the information on the internet, but it may be difficult to know what to use. Can I answer that in just a second? Yeah. What I think, and somehow the chat feature disappeared, so I'm not seeing it. There we go. So stronger acids have lower pKa. Oh yeah, stronger acids have greater Ka, smaller pKa equals loses proton. Good, there you go, that's a good summary. So we just need to compare this number 16 with numbers over here for our various acids, and if the number's less than 16, yes, the base can remove that proton. If it's higher, then no. Now, how do you recognize these functional groups? Because ultimately you're going to be given for information a table that is general, necessarily general, and isn't going to resemble that much the molecule that you're looking at, other than it's going to have the key functional group. As an example, a carboxylic acid is going to be on the pKa table like I've drawn it here with a pKa of 4. Now, R means that could be anything, all right? And so you need to be able to look at the table and then look up here in the structure and say, this has the same functional group. There's a bunch of stuff over here, but I was told that could sort of be anything. So to a first approximation, that's the pKa to use. Is that the ones that people get mixed up on without are the ones that can have multiple acid-base equilibria. For example, alcohol 16, protonated alcohol -2. So, if you look at if there were some alcohol in our molecule, you would need to say to yourself, okay, well, I need to pay attention to this one, the one that's 16, not its conjugate acid. I'm trying to think. Another situation that sometimes trips people up is on a pKa table, it will be written that this has a pKa of 38, where R is and I hesitate to say what R is because you may want to say it can be anything, but actually it's not. The pKa is different if there's a carbonyl adjacent to the nitrogen, or if there are other things that are not sort of hydrocarbons adjacent to the nitrogen. So, for example, these two have different, that I've just drawn, have different pKa's than just a regular amine. So what you're going to want to do is look on the table that you've got in the book or the information that I give you for the thing that most closely resembles the functional groups your molecule has.
So R's are only hydrocarbons.
Sorry?
R is just only hydrocarbons.
It's a good bet that the pKa won't change a lot if you assume R is a hydrocarbon. As an example, I told you that alcohols typically have pKa's around 16. But look, here's an alcohol, and it doesn't have a pKa of around 16. It's got a pKa way less than that. The reason for that is resonance stabilization of the conjugate base, which I'm just going to draw one portion of the molecule here, but by resonance, I can delocalize that negative charge here, here, and there. So it's not just a regular alcohol, it's a resonance stabilized, it's got a resonance stabilized conjugate base. And so if I were trying to look up a pKa of this alcohol, I would look for something on my table where the OH was attached directly to the benzene ring. So focus on the functional group, but also be aware of context and look for the thing that's most similar. Let's see. Trying to think if there's any other clues. You want to ask a follow-up question? Anything I can? Any others that I can answer there? What do we got on the chat? Why not just put all things, the information we need in the question? This is OChem not looking things up class. Fair enough. But if you don't want it to be looking things up class, maybe we should just make it closed book, huh? No, no, no. All right. Oh, no. I think I probably know what F means, but I just want to point out that BYU is not responsible for the statements of people on chat, and that this is neither endorsed nor encouraged by BYU or its sponsoring institution. Okay. Was that enough? Was that enough of a disclaimer? I think we're okay. I don't think he heard you. Oh, well. That's getting funny. All right. Maybe we need to turn off the chat. Okay. Is there something I'm missing? I'm hearing somebody chiming in on audio. What's up?
Yeah, sorry. I was asking a question. Can you hear me?
I can hear you now.
Okay. I was just wondering, so with the OH value, the alcohol that went down from 16 to 10,
Yeah.
how can we know the specific value of the pKa without having it memorized, I guess?
Okay, so the question was if in the example above where we had an alcohol whose pKa was lower than what we expected, how would you know that without memorizing it? Well, I would not expect you to know that the pKa of this alcohol attached to the benzene ring, it has a non-systematic name which we'll call phenol. I would not expect you to know that the pKa is 10. However, if I asked you instead, without pKa information, compare these two acids and tell me which is stronger, the way you would answer that is to draw the conjugate bases and then compare them and say, what is the difference between those two conjugate bases? They're both, the negative charge in both cases is held on an oxygen, so there's not a difference in electronegativity. However, you can draw resonance structures that delocalize the negative charge from that oxygen onto some of the carbons of the benzene ring, and you can do that through the negative charge 2-step illustrated there, and if you follow that procedure, you can identify that the lone pairs can be on the atoms that I've just indicated there. So this negative charge from the phenol is stabilized by resonance, and therefore you would predict that the phenol would be more acidic, even if you didn't know the pKa's. So I consider that kind of question where I ask you to use information you have, or rather use trends and principles that you know to say whether one thing is more acidic than another. I consider that fair game because you shouldn't need pKa information to make that conclusion. Yeah?
Do you know where in the book we find like the pKa table?
Where in the book can you find the pKa table? There should be one in chapter 2 somewhere.
Appendix A.
Index A at the back of the book. Appendix A will have a bunch of pKa's at the back of the book. Thank you. That's tremendously helpful. So chapter 2 will have one. I don't remember on which page. Appendix A will have one. Usually when I give out written exams in the testing center, the pKa is the last page of the exam. If you like, I can have a PDF on the content page of Learning Suite that'll be relevant pKa's. Yeah? Okay.
So Professor Price,
Yes?
just to follow up with that, so in the question that you asked above, like you said that might be like an exam question.
Yeah.
How would we answer that? So, because we know that the alcohol would be more acidic, but if we like don't know the exact value, how would we know that it's
Well,
more
so
acidic than the one we were given?
the one up here, you would have to have the
Yeah.
pKa information to answer that. Although
Okay, so
I
we would
suppose,
probably be given that.
yeah, I suppose you could reason that, well, because of resonance, this should be more acidic than this alcohol. So if you can choose one acid is stronger than the other, then you already know that the conjugate base of that acid can deprotonate that one. But
Yeah,
for this
that makes
question,
sense.
you would have pKa information. Likely, if I ask this question, knowing you're going to have pKa information, it doesn't make a lot of sense for me to ask which is more acidic. Instead, I might say one is more acidic than the other, or I'm sure you can figure out which one is more acidic. Why is it more acidic? And then you got to choose the answer there.
Okay, perfect. Thank you.
Could I maybe do an example of a molecule with a ton of resonance structures again? Oh, and that's a great question. What if one of the acids has a pKa that matches the one of your base? Yeah, it's a good question, and we always encounter this one. So let's just take our example and let's put a regular run-of-the-mill alcohol in there with a pKa of 16. What are you going to do when pKa's match? Well, if they match, the equilibrium constant should be close to 1, which means sort of 50-50. Means if you had, it means whatever this base is could maybe deprotonate a maximum of half of this alcohol. How can an alcohol be half deprotonated? We're talking about half of the molecules in solution. And that's why I added this mostly here. Because when I've asked this question before, a gazillion years ago when I first wrote an exam, I confused a lot of people, and it was a written exam, and there were regrades, and it was miserable for everybody involved. I always regret misery on the part of the students. I always figure my own misery I deserve. So if I write test questions that are mistaken or funny, I can always go back and correct them. And in fact, multiple choice and Learning Suite enables me to do that really quickly, really easily. However, yeah, the way I've clarified that is I'm going to ask which protons can be mostly removed, where mostly is greater than 50%. Okay? So, I suppose for this question, we would say, no, that OH group isn't going to be completely deprotonated. Does that address the question? Yeah? And okay? Okay. And it does depend on what you want to know. There are some cases in OChem when you want to use a base and you want it to react somewhere but not somewhere else. And in that case, 50-50 is probably not good enough, right? If I were trying to use this as use ethoxide as a reagent and I really, really did not want to touch this OH group, I've got a problem. Even though it's not going to be completely deprotonated, it is going to interfere. We'll talk about that kind of thing, I think, later on, maybe not till 352. All right, any other questions on acid and base stuff? So this is one example of the kind of question you might get. The other is really the one we sort of talked about at the end of the last lecture. If you're given a biomolecule, can you predict what state each of the side chains should be at a particular pH? And remember, the principle there is you compare pH with pKa. If the pH is lower than the pKa, that proton is still on. But if it's higher than the pKa, that proton is off. If you want to, I don't like this, but if you want to, you can think of pH as telling you the capacity of the solution of water to protonate stuff versus not protonate stuff. When pH equals pKa, it's 50-50. When pH is greater than pKa, water's basic enough to remove the proton. When pH is lower than pKa, the proton is still on. All right, so be able to do that. In particular, I think this kind of question is not necessarily on your practice exam, but I think you should be able to do it based on the information we've given you. Okay? So maybe write your own question. Maybe take a bunch of acids from the pKa table and ask yourself, at pH 7 or at pH 14, well, let's not go crazy, maybe pH 10 or something like that, or pH 2, what would this acid be in aqueous solution, and see if you can do that. Okay. All right. So now I want to spend a little bit of time on stuff from Chapter 3. Chapter 3 includes nomenclature, naming organic molecules. All right? Your goal here is twofold. First, you want to know enough that as I talk about organic molecules in class, you're not lost. Second, you want to be able to write a name that specifies a molecule completely enough that someone who reads the name won't draw the structure incorrectly. In other words, your goal is to be completely unambiguous. Now, a word of warning about nomenclature. There is a committee of the International Union of Pure and Applied Chemistry that makes the rules for naming molecules. But it's not like this is a fundamental principle of our universe. They're getting no revelatory direction from anybody. They're just making up rules that seem like they work. And you can always come up with a more complicated situation that would be more difficult to name. I don't want you to get caught in the but what if trap, because you can always make a question I might give you unanswerable by making it more complicated. Your goal is to be able to understand when I talk about molecules and to name molecules unambiguously. Understand that the questions are going to be multiple choice, and so you're not exactly going to be naming structures from scratch. There are some things that it's useful to know, and there are some other things that it's useful not to know. So I'm not going to spend a lot of time talking about the rules. I feel like you can get that from what's in the study guide. But here's a couple of helps to guide you in what to spend time on and what really not to worry about. Priority. The highest priority functional group is the one that determines the suffix for the compound's name. For example, if the molecule is a carboxylic acid or has a carboxylic acid in it, there's going to be a bunch of stuff here, and then it's going to end in the suffix for a carboxylic acid, which is oic acid. For example, if this molecule, if the R group were just a methyl group, there are 2 carbons, we would call this ethanoic acid. F because it's got 2 carbons, AN because there's no carbon-carbon double bonds, and oic acid because it's a carboxylic acid. By the way, nobody in their right mind calls this ethanoic acid. They just call it acetic acid because that's what we've called it forever, or better yet, vinegar. Now, there are a bunch of other priority functional groups that have similar numbers of bonds between carbon and oxygen. And I'm going to list them here in no particular order of priority. Esters, amides, acid chlorides, acid anhydrides. And it's useful to know the suffixes for all of these. But some people ask, do I need to know how all of these rank in priority? And the answer is really not. Because for most of the molecules you will encounter in naming questions, if it has anything from up here, it will be just 1. All right? So in that case, it's good enough to recognize that if you have a carbon bonded the same carbon bonded 3 times to a heteroatom, it's probably in this priority 1 group. All right? So this is like airline boarding. If you're in the priority 1, welcome to our platinum flyers or whatever like that. You get to go first, but they probably don't care whether you're in seat A1 or seat A2, right? Similarly, we're not going to care whether acids or esters are higher ranked than each other, because for most of the molecules you'll encounter, there will be only 1 of these. That's not to say that there aren't molecules that have multiple of these functional groups, only that we won't even dare to try to name them because doing so would be pointless. I mean, honestly, if you want, there's a program called ChemDraw that you should have access to through the OIT software page as a BYU student. You can draw a molecule in ChemDraw and you can tell it to name it for you. Bing! You got the right name. So if a computer can do it, then that means we probably don't need to think about it anymore until our robot overlords, again, take over and deprive us of access to computers. And then we'll start memorizing things again. The second priority group is sort of 2 bonds to a heteroatom. By heteroatom, I mean anything not carbon or hydrogen. As an example, you've got the ketones. And this is where the use of R groups is tricky, because for ketones, they really do have to be hydrocarbons here, though not necessarily what I've drawn. So where R equals hydrocarbon, or aldehydes. It's useful to know the suffix here, "-one" for the ketone and "-al" for the aldehyde. For both priorities 1 and 2, it's not that useful to know the prefix because I just told you that we're unlikely to be in a situation where one of these isn't the highest priority functional group in your molecule. The prefix for the ketone and for the aldehyde is both oxo. So if you had a carboxylic acid like this and you had a ketone on that carbon, you would call this, let's see, hexanoic acid, and you'd put 4-oxo on there, and then everybody would know what you were talking about. And then finally, you have priority 3. In many cases, these are not the highest priority functional group, 1 bond to heteroatom. It's not necessarily that important to know within this group, which is the highest priority group, but you should know suffixes and prefixes. An example, if you've got an OH group attached to a hydrocarbon, it's called, the suffix is -al, and the prefix is hydroxy, and so on. Okay? Yeah?
What was the suffix for this priority 2?
Suffix for the ketone is -one. Suffix for the aldehyde is -al. All right. So hopefully that saves you a little bit of time in terms of what you memorize versus what you don't worry about. Something else not to worry about. Numbering schemes. All right, now technically, you give the highest priority functional group the number 1, and then you number down the chain from there. And if you have a choice in which direction to go, you choose the direction that gives all of the functional groups the least possible numbers. But that gets kind of dicey, and in any case, people quickly start to ask, but what if it's a cyclic compound, and how do I know which way to go around the ring? And the answer is, I don't care. Technically, this is 3,4-dimethyl-cyclohexanone, because technically I number it this way. But if you numbered the other way and said it was 4,5-dimethyl-cyclohexanone, I'm fine. I'm not going to get any arguments from me. Okay? And then the one thing that is really important that you work on is E and Z stereochemistry about alkenes. Technically, this isn't a thing until chapter 10, but I'm choosing to introduce it now. The study guide 3 takes you through it in a lot of detail, and it's just easier to do now with nomenclature. And what we do here will be useful when we get to the chapter on stereochemistry. So, as we mentioned before, rotation is restricted about carbon-carbon pi bonds. And the reason for this is that you have to basically break the pi bond and destroy the side-to-side overlap between p orbitals on the carbons that are involved in the alkene. If you don't believe me, we can go look at, oh, Adam's been playing Among Us again. Did you know that GG means good game? Didn't know that. I'm learning things. Adam's also been watching YouTube. I wonder what we're looking at. Auto-tune versus no auto-tune. Okay. Adam tells me that Adam Levine's not that good when he's not auto-tuned. I don't know based on his Super Bowl performance, I would agree with that, but we like him anyway. Messages. Oh, okay. Sorry. I wanted to go personal life. I wanted to go to this fun iPad app called Molecules. And this has, among a lot of other things, it has some shapes it has some molecules that we can click on and see how they actually sort of move around in solution. I got to find one with a double bond. Dun, dun, dun. I think EFGHI. Indigo. All right. This molecule is called indigo because I guess it's purple. What you're seeing there, red spheres are oxygen atoms, blue spheres are nitrogen, white spheres are hydrogens, and black spheres are carbons. The purple represents electron density, average electron density for all of the occupied wave functions in the molecule. And you can see, as you would expect, they're sort of just hovering around where the atoms are. There's a double bond in the middle. One of the cool things about this app is that this is an actual what's called molecular dynamics simulation. You can you basically treat each of the bonds as springs and each of the things on the edges of the bonds as charges, and then based on that and some information about bonds, you basically treat it like a Newtonian sort of system, and you can make the molecule wiggle, and if you give it kinetic energy, it'll do some interesting things. I can add to the kinetic energy of the molecule by turning up the bath temperature, and then you can see it starts to wiggle a lot. But you know, at those temperatures were thousands of Kelvin. That's probably not good, so we'll cool it back down to room-ish temperature. 317 is too hot, 298-ish, a little colder than room temperature. All right, so at this temperature, you can see that we started out with the two nitrogen groups opposite each other. And you're going to see that I actually have to try really hard to get it to rearrange. All right, now I was able to do that because I grabbed onto one side and held onto the other and pulled. But there's an energy barrier there, right? If I cool it down so that the molecule has even less kinetic energy, and then I try to do it, there's no rotation, right? And this is in contrast to a molecule where there might be methyl groups on it. A sigma bond, you can rotate around it really easily, no problem, even when the bath temperature is 50 Kelvin. Instead, if I go to indigo at 50 Kelvin, it's just not rotating, right? So because we don't have rotation around double bonds unless you break the pi bond, we've got to have a way of talking about the two different options. The options where the oxygens are on opposite sides or the nitrogens are on opposite sides versus the option where, let's see if we can do it, boing. It's just kind of fun. It helps you see molecules in a way that they don't appear on paper. We have to have a way of talking about those two different options because they are different, right? One of them has the two nitrogens on the same side, one has the nitrogens on opposite side, and that difference in shape can dramatically influence function. Remember that it was isomerization about a double bond, which we talked about as being an important part of vision. A change in shape makes a big difference. So how do you talk about shape about a double bond? Is that Theodore Gray Molecules app only on the Apple Store? I don't know. Good idea. Good idea to ask? I don't know. Somebody can check the Android store. So double bond with all hydrogens, nothing to talk about. There's no alternative shapes, okay? Double bond with two of the same thing on the same carbon, still nothing to talk about. Even if there's different things on the other carbon, we'll call carbon 1 and 2, because there's two methyl groups here, it doesn't matter whether I put the methyl group on carbon 1 down or up, I get the same thing. If you can't see that those things are the same, then you need to practice with your spatial reasoning. And to do this, you need a molecular spatula. Oh, dang, I need gray. But don't cut yourself. Some spatulas are sharp. Don't like those. But I also don't like the spatulas that, like when you cook eggs, the eggs get like stuck to them and you're having to scratch it with your, maybe you don't experience this. Anyway, sorry. Put your spatula under the molecule and flip it over. It's the pancake flip operation. Slide it under there and ka-thunk. Oh, I did the wrong one. Slide it here and then flip it over that way and it's the same thing. Can you see it? Yeah. So nothing to see there really in terms of different shapes, identical shape. It's when we have two different things attached to carbon 1 and two different things attached to carbon 2 that we then have something to talk about. So let's put CH3 here. That is not the same as this. Not the same shape at all. Carbon is bigger than hydrogen, so this one's going to have sort of a curvy shape, whereas this one's going to have an extended shape. Both of these would be called 2-butene, but they're different from each other. So what do we do? And the answer is, well, it could use cis and trans. And in fact, when both carbons only have one group other than hydrogen, cis and trans is just fine. So we could call this cis 2-butene and trans 2-butene. Trans being across, cis being same side. All right? But that will break down if we start having some non-hydrogen things attached to, that will start to break down if one or both of our carbons is attached to two things other than hydrogen. So all we have to do to make this a little bit more complicated is to add another couple of carbons to carbon 1. Okay, carbon 1, carbon 2. All right, now what do we do? Well, if we were going to name this, I don't know, 1, 2, 3, 4, 5, pentene, and it would be like 3-methyl in both cases. Okay, but how do we describe the fact that in this one, methyl's on the same side as methyl, whereas in the one on the right, methyl's on the same side as that larger ethyl group? You can't use cis or trans because cis and trans are relative terms. And so if I called this on the left, if I tried to call this cis 3-methylpentene, somebody trying to draw that would not know that you meant that the methyl groups are cis to each other. They might also think that you could interpret it another way. So we need a new system. And similarly, if you tried to call the one on the left trans 3-methylpentene, they wouldn't know that you meant the methyl groups are trans to each other. So we've got we need a shortcut way of saying that without all of those words. 3-methylpentene where the 2 methyl groups are cis to each other. That's entirely too many words. So we've come up with a very, very complicated system to use a single letter to tell which option you want. Okay? And the letters are E and Z. So, because I know the answer, I will tell you that the alkene on the left has an E configuration, whereas the alkene on the right has a Z configuration. So, what I want you to do before next time is I want you to go learn the rules for choosing how we assigned E versus Z. I will give you a hint. E is from the German Entgegen, I think, and Z is from the German zusammen or something like that, which relates to, I think, opposite or together or something like that. Anyway, learn the rules and we'll do some examples next time. Oh, and for the folks asking at home, I don't have a problem if you use iPad apps like the one I showed you. I can't imagine it would be terribly useful to you, but it, in the same way that a model kit might be useful to you to visualize organic molecules, certainly I don't have a problem with you using that app.